Hey guys, this video is on stoichiometry. So let's define that first. Stoichiometry is the study of the relationship between quantities of substances involved in a chemical reaction and the substances that are produced as a result of that chemical reaction. So what that means is how much of this reactant is needed to react with this other reactant to make this much product, basically. All right, so let's get into it. The first thing is the whole idea behind stoichiometry is that when you have a balanced chemical equation, the coefficients, the numbers in front of the formulas, give you conversion factors. So, yeah, that's right. I am talking about dimensional analysis. And I misspelled that, but I'll fix that. So, for example, in our generic equation, AA plus BB goes to CC plus DD. You're going to see this kind of thing a lot in chemistry. This says, this is just the form of a chemical equation where the lowercase letters are the coefficients, the numbers in front of the formulas, and the capital letters stand for the compounds, the formulas of the compounds. So we get a lot of conversion factors just from this. There's between pick any two species in here, and there's a conversion factor given by the ratio of the coefficients, for example. And we think about it usually in terms of moles. Grams doesn't work, that's the thing. It has to be moles or numbers. So A moles of A equals B moles of B. In other words, what that's saying really is that in this particular reaction, A moles of A react with B moles of B. A moles of C equals C moles of C, meaning if you start with A, lowercase a moles of compound A, you can produce C, lowercase c moles of compound C. Likewise, A moles of A produce D moles of D, B moles of B produce C moles of C, B moles of B produce D moles of D, and if C moles of C are produced, then we also get D moles of D. Now, that's a lot of conversion factors. We almost always only need one of these. Which one? Well, the one that's going to help you answer your question, basically. You'll see. So, for example, given the following balanced equation, how many moles of aluminum are needed to react with 0.3141 moles of zinc? So this is dimensional analysis, which is a type of stoichiometry is a type of dimensional analysis. And so in terms of dimensional analysis, the units of our answer will be moles of aluminum, and our starting point would be 0.3141 moles of zinc sulfate. The only conversion factor we need of all those ones that we get from looking at this equation is the one that connects the two things that we care about. In this case, aluminum and zinc sulfate. So from the balanced chemical equation, we see that 2 moles of aluminum react with are equal to 3 moles of zinc sulfate. That's the only conversion factor we need. So we take it down here, make sure everything cancels out correctly, and we get our answer, 0.2094 moles of aluminum. Now, however, usually we don't have moles, right? Because we can't measure moles directly in the lab, but we do have grams. So this is a more typical type of problem that you'll see right down here. How many grams of water can be produced by the reaction of 5.199 grams of methane, which is this stuff right here, with excess oxygen in the following reaction? Don't worry about me saying excess oxygen. That's just kind of being technical, so we don't have to worry about something called limiting reactants, which we'll see in a little bit. But I think it would be a good idea if you guys just stop the video right now, go ahead and see if you can work this problem out on your own, and then come on back when you get an answer. Welcome back. So, dimensional analysis. We want to know how many grams of water is equal to, can be produced from 5.199 grams of methane. Now, the conversion factor at the heart of the stoichiometry comes from the balanced equation. If you go look back at that, you'll see that the coefficients tell us that 1 mole of methane produces is equal to 2 moles of water. We know we're going to have to use that. See, that's the only connection we have between these two different compounds in this problem, methane and water. So we have to use it. And so what I do is I write that down first, and I say, okay, what else what do I need to use? What conversion factor do I need to get here so I can use this? And then what do I need to get to my answer, my units of my answer? Well, we're starting with grams of methane, and I need to get to moles of methane to use this. And the conversion factor, we do it so much, you should memorize this. that to convert between grams and moles and grams, we use what? Molar mass. So I'm going to need the molar mass of methane so that I can convert the grams of methane into moles of methane so that I can use this conversion factor right here. And so that's what I wrote down here. I wrote the molar mass of methane as a conversion factor. 1 mole of methane is equal to 16.043 grams of methane. All right, great. So that lets me go from grams of methane to moles of methane to moles of water. But I want grams of water, right? So now I need, guess what? The molar mass of water to convert from moles of water to grams of water. And that should do it for me. So then I come down here, set up my equation, starting point, make sure the units of the grams of methane cancel. So I use this one right here, gives me moles of methane on top, cancel moles of methane, gives me moles of water, and then moles of water cancel, gives me grams of water. And I get my answer, around 4 sig figs, 11 point, in this case, because of the 5.199, by the way. 16.043 is 5, the 2 and 1 are exact, 18.015 is 5 sig figs. So 11.68 grams of water is my answer there. All right, so limiting reactants. In real life, when you perform a chemical reaction, no matter how carefully, guys, no matter how carefully you weigh out both reactants, one of them is going to run out first. Okay, you can't measure exactly the same exact number of atoms or molecules you need of each one. Whichever one runs out first is the limiting reactant. Now, once one of the reactants is used up, the whole reaction stops. So it's limited by the limiting reactant, the one that runs out first. So we're going to need to find the limiting reactant. By the way, you'll see this in a minute. The red flag, the clue that tells you that you're going to have to first find a limiting reactant is this. You will be told somewhere in the problem how much of both reactants you start with. If you see that, then that tells you right there, before you can do anything else, guys, you're going to have to find the limiting reactant. And I'm going to show you how to do that right here. So a little tiny procedure to find the limiting reactant. First, find moles of all the reactants, and do that however you can. At this point, it's usually going to be converting grams to moles using the molar mass. But as we go through the course, we'll see that we can be given this information in other ways. So basically, do whatever it takes to find the moles of all the reactants. Then, the moles of each reactant that you found, divide that by its coefficient from the balanced equation, the number in front of its formula in the balanced equation. Whichever of those reactants gives you the smallest answer when you do that division, that's the limiting reactant. Easy. Done. Okay, so let's use this. So let's say 2.179 grams of zinc react with 2.224 grams of hydrochloric acid. Well, actually what this is saying is we measure out 2.179 grams of zinc and weigh out 2.224 grams of hydrochloric acid. Just at this point, just find the limiting reactant. So again, what you guys should do is pause the video, try to follow that procedure that I just gave you and see if you can find the limiting reactant. And just remember, to go from grams to moles, you need to use the molar mass. Divide by the molar mass. All right, welcome back. So I'm going to take the mass given of zinc, divide by its molar mass, gave me that many moles, divide by its coefficient, which is 1, so I get the same number, 0.03332. And I don't write units here because these are just to find the limiting reactant. And by the way, we're going to throw out these numbers once we find the limiting reactant. These numbers are worse than useless to you guys. Throw them out. If you keep them around, they're going to hurt you. Okay. So I found this for zinc. Doing the same thing for hydrochloric acid. Take the grams, divide by the molar mass. I got this many moles of hydrochloric acid. Its coefficient's 2, so I divide by 2, and I get 0.030498. This number is smaller than this number, so that tells me that hydrochloric acid is the limiting reactant. Once I find that, I'm going to throw this number out. Okay, get rid of it. I'm going to keep this number. It's a good one, but this one's bad. All right. Now, okay, the reason that we find the limiting reactant is because then we can now continue on and perform our stoichiometric calculations, our dimensional analysis. And so this is something that's going to really help you guys if you remember it. That's why I put it in red up there. The moles of the limiting reactant is always the starting point for the stoichiometry, the dimensional analysis. And I'll show you what that means with this example right here. So How many grams, so this is the problem. We want to find out how many grams of gold metal can be produced by the reaction of 3.414 grams of copper with 9.599 grams of gold 3 chloride, this stuff right here. So nothing is said, right, in here about limiting reactants, but what tells you the clue, the flag, that tells you that the first thing you're going to have to do before you can do anything else is find the limiting reactant, is you're given the amounts of both of the reactants, copper and gold 3 chloride. All right, so I want you guys to give this a shot, see if you can figure it out. Pause the video, come back when you get an answer. Welcome back. So, first finding the limiting reactant, just like we did in that previous problem, we take the grams, divide by the molar mass. So 3.414 grams of copper divided by its molar mass gave me 0.053724 moles of copper. The coefficient for copper is 3, so I divide by 3 and I get this number. Same thing with gold. This number here down here, guys, this is the molar mass of gold 3 chloride. I calculated this by adding up the molar mass of gold plus 3 times the molar mass of chlorine. And I get this many moles of gold 3 chloride. When I divide by 2, which is its coefficient, I get this number. Comparing these two numbers, this is smaller. That means that we know that gold 3 chloride is the limiting reactant. But once we know that, guys, get rid of this number. Throw it out. It's useless. It's worse than useless, okay? But this is a good number. Keep it. We're going to use it. This is our starting point for our dimensional analysis, our stoichiometry. All right, so we're not done, right? All we did was find a limiting reactant. Now we have to answer the question, how many grams of gold can we get from this much gold 3 chloride? But that's easy. That's just dimensional analysis. So, you know the units of our answer is grams of gold. Starting point, remember always moles of limiting reactant. So there it is. Conversion factors from the balanced equation. Mole-to-mole ratio between gold 3 chloride and gold. In this case, it's 2 to 2 or 1 to 1. Gives us that connection. And then to get grams of gold, once we get to moles of gold, we just use its molar mass. So this number here, guys, this is the molar mass of gold written as a conversion factor. Setting up my equation, moles of my limiting reactant, make sure the moles of that gold 3 chloride cancel, gets me moles of gold, gold to mold. And then use the molar mass, moles of gold cancel, and I get my answer, 6.233 grams of gold. That's all there is to that. All right, one more thing, guys. Percent yield. So percent yield, I mean, the name kind of gives it away, is the definition, the formula, is your actual yield over theoretical yield times 100. Now, what this is talking about here, guys, is in real life, when you perform any chemical reaction, you'll never get exactly the yield that you calculate, like we just did, that you could. There's always some mitigating factors, side reactions, loss, there's always loss, right? There's always some reason why you're not going to get your 100% yield. So what we do a lot is we calculate our percent yield. So how much you actually get, how much product you weigh at the end of the experiment, that's your actual yield. That's a real number you get in the lab. In terms of problems here, you have to be given that number. The theoretical yield, that's what you calculate. So remember, you always calculate the theoretical yield just like we did the past couple problems using the stoichiometry, dimensional analysis. So let's say in that problem we just did with the gold and the gold 3 chloride, we did that experiment and we weighed our product at the end and we got 5.734 grams of gold. To calculate the percent yield, we just take how much we got, divide by what we calculated the yield would be. We just got this number times 100 and it ends up 91.99% yield, which is actually really pretty good. Anyway, that's all there is to that, guys.